Chapter 10, Thermal Physics in College Physics. Thermal, of course, from the Greek word for heat. So we're going to be talking now about not just the qualitative observations about heat and its effects, but also figure out a way to be able to measure the quantity of heat. We can look at heat from two different perspectives. We can look at it from the macroscopic level and from the microscopic level. Both of those are going to give us information that helps us to have a complete picture of just what is heat, how does it get from one place to another, what's responsible for it, how are we going to be able to measure something that we call temperature. Hopefully you remember from chemistry that temperature is the measure of the average kinetic energy of the particles of a substance. So if you go all the way back to the foundation of chemistry, and that is that everything is made out of little teeny tiny particles that, depending upon whether they're solids, liquid, or gas in that state, those particles are moving around or vibrating, colliding with each other perhaps, maybe spreading out, maybe coming together, experiencing intermolecular forces, experiencing attractions of opposite poles. And all of this different kind of motion is kinetic energy. And of course, some particles could be moving very, very fast. Other particles might be moving very slowly. Even in the air of the room that you are in right now, there might be a few particles traveling very slowly across the room. The technical term for that is lollygagging. And you might have some other particles that are going extremely fast across the room. That technical term for that is they are really boogieing. And so when we talk about the temperature of the room, we want to measure the average kinetic energy of all of these particles. Another factor of this is that some particles could be moving to the left and some to the right. If we remember that velocity is a vector, that would mean that those two velocities in opposite directions, if they were the same, would cancel each other out. And you could theoretically say you have zero kinetic energy. The same could be said for particles moving up compared to down or in compared to out. And so we talked about the absolute value of all of these velocities, and then we take the average of those velocities, and that is proportional to the temperature of that substance. There's different ways to calibrate and talk about temperature, which we'll get to in a little bit. Now, everything about heat, including the three laws of thermodynamics, turn out to be predicated upon something that is even more foundational and is now called the zeroth law of thermodynamics. And that is basically the observation that the net movement of heat is to go from something that is hot to something that is cold until they reach the same temperature. As long as things are in thermal contact, that means heat will go from the warmer to the colder. Now, some particles might go in the reverse direction, so we are talking about the net change. The net flow of heat is from warm to cold until you reach thermal equilibrium, in which case there's no longer any net exchange of energy, even though energy is going in both directions at the same time. And now both sides have exactly the same temperature. When you reach thermal equilibrium, if you're an organism, that basically means you reach room temperature, which of course for warm-blooded organisms would actually be death. And you hate it when that happens. Unless, of course, it's like a mosquito or some other obnoxious organism that is bothering you. So the exchange of this energy is called heat, and we use a thermometer in order to measure the average kinetic energy, which we call temperature. Now, if you look at the word thermometer, you obviously see the term thermo, meaning heat, and meter, meaning measure of, if we do the etymology of this science word. And you're used to using probes like this that can connect to LabQuest. Some can connect directly to an iPad. And they're based upon the fact that you've got a couple of different metals in this probe that are going to respond differently to heat, and that enables the instrument to calibrate the amount of heat that would create the kind of difference in those metals. We'll talk about conventional thermometers in a little bit. Excuse me. So the zeroth law of thermodynamics, otherwise known as the law of equilibrium, is right here. If you have two objects, A and B, and they are in thermal contact, which means there's not an insulator or barrier between them, the heat will go from one to the other until they are at thermal equilibrium, meaning they have the same temperature. And eventually they'll have the same temperature as their surroundings. So let's talk about thermometers and temperature scales. One kind of thermometer that you're very used to, pictured over here, is going to be a very, very thin tube that has an opening running down the length of it, an empty capillary tube. At the bottom of it, we put some type of liquid that's going to expand up the tube when it's in warm environment, and it contracts and therefore goes down the tube when it's in a cold environment. And all we have to do is put numbers along the side. And again, we'll talk about that in just a minute when we have a picture of three thermometers with three different scales. Typically, we use the Celsius scale, also known as the centigrade scale. And if you look at the word centigrade, obviously we mean there are 100 gradations, 100 divisions between freezing and boiling. Very convenient number. And you should know the freezing point and the boiling point of water on the centigrade scale, 0 and 100, and I know you all know that. Your everyday use, in America at least, we often use the Fahrenheit scale, 32 and 212, which would have 180 divisions between freezing and boiling, and that's kind of awkward and inconvenient. Here's a fancy kind of thermometer that we're not going to talk about very much. It's one, again, that we can calibrate by putting ice over here to achieve one level of the material that's inside our tube, and then we can warm it up to find another level, and then we can look at this difference in height in order to calibrate that to come up with a temperature scale. What I do want to mention, though, is that pressure and temperature are intimately related, especially for gases. And therefore, if you look at this graph down here, and this is a pressure versus, temperature graph, you can see if I was able to measure, say, the pressure at 100 degrees boiling of a liquid, let's say water, and then I cool it down to 0 degrees, which is freezing, and I measure the pressure there, I can establish a line, a y equals mx plus b. And then if I extrapolate it on downward, ostensibly getting to the point where the pressure becomes less and less and less until the pressure approaches 0, meaning the particles aren't moving anymore and colliding with the inside of the container that they're in. That would be the absolute minimum pressure you can possibly have. You can approach it. There will always be some motion to the particles because of quantum physics, but that would be the absolute limit of the pressure. So when we look at what the temperature is, when the particles basically stop moving in any translational or vibrational or rotational way, we get the number negative 273.15. We call that absolute 0 to 5 significant digits, and that would be on the Celsius scale. We would call it 0 Kelvin on the Kelvin scale. Notice that 0 Kelvin does not have the little degree sign. We have that little degree sign for Celsius and Fahrenheit. We don't use it for Kelvin. And each degree on the Kelvin scale is called a Kelvin. So at absolute 0, we have 0 kelvins. At freezing, we would have 273.15 kelvins. At boiling, we would have 100 degrees more than that, 373.15 kelvins. We can also find a point at which, with the right pressure and with the right temperature for a pure liquid, we could find a situation where a pure substance could exist as a liquid and as a solid and as a vapor all at the same time. It would be very unusual for a temperature such as that to be present in the environment, but you could have the right temperature-pressure combination where you would have what is called the triple point, where you have all three states of matter coexisting at equilibrium. Certainly on a winter day, you can find places where you might have some liquid water, some water vapor in the air like clouds, and some frozen water like snow or ice all at the same time. And it is a way for calibrating what a Kelvin might be. Here are some important temperature values on a logarithmic scale of powers of 10. So right now we have been able to reach temperatures that are basically approaching a trillionth of a Kelvin. That's pretty cold. And liquid helium, He, is a little bit more, is about 10 to the 10 to the 0 power. Liquid hydrogen, because it's a molecule, and therefore you have some energy tied up in the in that bond holding it together, is 10 to the first power. Water freezes at around 32, and this, by the way, is on a Kelvin scale, 32 Fahrenheit, or 0 Celsius, or 273. So 10 squared is 100, and so when we're up here, we're about 212 Fahrenheit. And then it goes on and on. We got the surface of the sun, a solar corona emanating from the surface of the sun, the interior of the sun, and believe it or not, we have been able to create temperatures that we believe are hotter than the sun at the center of some of our atomic bombs as the result of fusion. Now, one of the things we'd like to do, if you think about superconductivity, is to find things that will superconduct. Maybe they're ceramics, maybe they're metals that will superconduct somewhere in this range, somewhere around room temperature. So it wouldn't take tremendous amounts of energy in order to keep the temperature, in order for the materials to superconduct. Now, we're not going to worry about converting to Fahrenheit to Celsius and Celsius to Fahrenheit. You would be given that equation on the test if you needed it. Here's our three temperature scales, and you can see this first scale, Lord Kelvin. He tried to use, he actually set up the scale so that the coldest temperature that he could reach using ice and water, like if he was going to be ice, water, and salt, like if he was going to be making ice cream, he called that 0, coldest temperature he could get in the lab. And up here, he called body temperature, originally 100 degrees Fahrenheit. So he had 100 divisions between the coldest temperature in the lab and body temperature. Now, finding the coldest temperature you can get in the lab is rather inconvenient because of the fact that you'd have to marshal your salt and your ice and all of that kind of stuff and put it together. And also, turns out body temperature kind of fluctuates for individuals, particularly if you have a slight fever. It's interesting to note that theoretically, way back when, if you had a normal body temperature, it was supposed to be 100 degrees Fahrenheit. But over time, we realized that the average body temperature is slightly less than that. Maybe 98.6, which is the first average body temperature I learned way back in grade school and high school. But since that time, since I've been teaching, now it's estimated at maybe being 98.4, and I've seen a lot of ranges on this, especially lower than 98.4 for individuals when they are healthy. Now back to the Fahrenheit scale, it's a whole lot easier just to freeze water and call that 0. And it's a whole lot easier to boil water and call that 100. And so now we have the centigrade scale, 100 divisions between freezing and boiling instead of 180 divisions here. So if you have ice water, you know it has to be 0 degrees. If it was any colder than 0, you wouldn't have any water. If it was any warmer than 0 Celsius, you wouldn't have any ice. So ice water, by definition, would be 0 degrees. The same with steam. If you have boiling water, and we're talking about at a sea level pressure, if you have boiling water, it has to be 100 degrees. Any less, it wouldn't be boiling. Any more, all the water would have turned to steam. Now, the Kelvin scale says, let's keep this. Let's keep 100 divisions between freezing and boiling, but let's go down and down and down and down until we get to absolute 0, and then count backwards using those Celsius temperature ranges, using the same scale right here, but apply it over to this thermometer here. So when you start at 0, by the time you get to the temperature at which water freezes, 273.15, 100 degrees later, 373.15. Notice that the change in temperature for Celsius equals the change in temperature for Kelvin. Please also note that anytime you're asked to find the temperature and it's in an equation like PV equals NERT, which you people in chemistry might remember, whenever you have just T in the equation, you have to use Kelvin. That's very important. It has to be Kelvin. But if you have delta T in the equation, and in a little bit we're going to get Q equals MC delta T, it doesn't matter whether you use Celsius or Kelvin. And here's some practice for converting from Celsius to Fahrenheit or back again, and that is very pedestrian for you all. And here is where we basically begin to think about the effect of heat on solids instead of liquids or gases. And again, solids are going to expand when they're heated up, and they're going to contract when they cool down, with one very notable exception, which of course we'll talk about at length later, water. And that's why we need these thermal expansion joints like that you can see over there. You can see them there. You can sometimes see a fibrous material in between sections of sidewalk or driveway made out of concrete. And what you should know, of course, is that how much a solid is going to change in length is going to depend upon 3 things. You either have done or will be doing a lab on this called the coefficient of linear expansion lab. And of course, the longer your piece of metal is, the more it can get bigger. And the bigger the change in temperature through which the metal expands, the more it's going to expand. And it also depends upon the nature of the metal itself. This is alpha for change in length, and we use beta for change in area, and we use gamma for change in volume. The thing to remember, and I think it's around here somewhere, is that when we use the change in area expansion, that's going to be 2 times the change in alpha expansion. And when we use the change in volume expansion, it's going to be 3 times the change of linear expansion, because volume is 3 dimensions and area is 2 dimensions. And so these math problems are pretty easy, and here you can see and compare some of the coefficients of linear expansion for different materials. You've all worked with Pyrex in the lab because it has a small coefficient of linear expansion compared to ordinary glass, which means it doesn't get that much bigger when it gets hot or you put hot water in it, and it doesn't get that much smaller or contract when you put it in cold water, which means the glass is not going to fracture or break. And we will demonstrate the bimetallic strip in a thermostat later in class, if we haven't already done so, and also show you this as well. But here you can see your 2 times alpha when we're talking about area. And then down here, we have the coefficient of area expansion and the coefficient of volume expansion.